Good day, everyone. It is nice over here for you and I because learning never ends and education is the key to an impactful life. My name is Anthony Nathaniel. I'm welcoming back to Global Education Zone. And in this particular episode of Mathematics for SS3, we'll be dealing with calculus. Now, calculus is that aspect of mathematics that deals with the change in the values of your x and y values of your a graph with respect to one another. So, for example, in calculus, you will be asked to calculate the respective or relative change in the y values with respect to the x values. Now, that's what calculus is all about. Calculus is just about the change, and that is why it's known as differential calculus. Now, in this particular episode of Mathematics for SS3, we'll be dealing with calculus in sufficient detail, and I'm going to break it down from the basics. Now, in the previous video of my in this channel, I talked about calculus in some detail, but not sufficient detail. But in this episode, we'll be talking about everything that you need to know if you want to start calculus from the scratch. Now, from the scratch, what you need to understand is that calculus deals with your graphs. So, if you want to deal sufficiently with calculus, you need to understand how to sketch and draw your graphs and how to calculate the changes, the gradients of those points. Now, basically, I mentioned earlier that calculus is all about change, right? Now, in other words, the gradient of a line is basically also about change. Though you might not have known, but gradient is basically a measure of the change of your y values with respect to your x values. So if you were to approach a line from a point, so what will be the change of your y with respect to x? And the answer is that change is x const and is defined by the tangent of the angle, or rather the tangent of that line, and that line will be called a tangent. So the tangent of that line, when it is drawn at that point in a curve or a line, that will be the gradient. Now, for a line, which we'll talk about in the previous episode of this series, we'll talk about lines and line geometry. We'll talk about gradients of lines. Now, when you're talking about lines, the gradient of that line is basically equal to the tangent, and it is basically a constant. But when we're talking about curves, such as parabolic graphs and quadratic graphs, cubic graphs, and equations, now for these specific types of graphs, we'll be dealing with gradient functions, and that is why we need to find the differential coefficient or the differential curve of a particular curve or a graph. Now, let me begin my explanation of calculus by this example. Now, in this particular example, I'll be talking about the graph, a particular equation given as y equals x squared minus x. Now, because the highest power of x in this equation is 2, that's why it's a quadratic equation, and as such, it's going to be a parabola when it is drawn on the graph. So let's talk about this question. And this particular question, we have that. So you can see the question on the screen. So basically, in this particular question, you have your table. So this table is basically a table of the corresponding values of the x and y coordinates of each point that passes through the graph or the curve. Now you can see that when x is minus 2, y is 6. When x is minus 1, y is 0. When x is 0, y is 0. You can verify this by plugging in your values of x, and you will get your corresponding values of y. So, and then each of these values and corresponding values, they make up the coordinates of each point on the graph. Now you can see that when you have this graph on the screen, you can see that it actually looks like a parabola. So in a subsequent video on this in this channel, I'll be talking about conic sections. A parabola is a specific types of conic section that has some properties which we're talking about, but not in this video. Now, in this parabola, you can see that now when we are looking for the gradient of the curve at the point 1, 0, all you need to do is you locate the point 1, 0. As you can see in this question, the 1, 0 is a point where you have your x coordinates as 1 and you have your y coordinates as 0. So it is basically that point 1. So when you draw a tangent to the curve at that point, it will give you the gradient of that point the gradient of the curve at that point. So the tangent to the curve at that point gives the gradient of the curve at that same point. Now, what I'm trying to say is that the tangent is basically that line that touches the curve at one specific point, and this specific point must be the required point whose gradient must be found. So in this case, when we are looking for gradient of the point 1, 0, that tangent must pass through the point P, which is 1, 0. Now, as you can see, when we draw that tangent, it is basically a straight line which must touch the curve only at that point. And even when you're making up the graphical method, you might not be very accurate. So that is why we make use of the differential equation and differential coefficient. So, and then we'll be talking about that. We're talking about the derivation and the expression. So, but first of all, let's talk about the graphical method. Now, you can see this line. This line, in the previous episode, I talked about the coordinate geometry, and we said the tangent, the gradient of a line is equal to the tangent of that line, and that tangent is the tangent of the angle which that line makes with the x-axis. Now, in these cases, you don't need to be looking for angles. All you need to make use of is the trigonometric functions. So you know that the tangent of a line is equal to the opposite divided by the adjacent, right? Now, in this case, you can see that the opposite is basically when you draw a straight line, a straight vertical line from any point on that on this tangent, you'll be able to calculate the tangent of the angle, and as a result, you'll be able to calculate the angle. So, but in this case, we'll only need to calculate the tangent of the angle because we're looking for the gradient, and the gradient of a line is given by the tangent of that line. So basically, we'll need to calculate the tangent value of this line. So now you basically make use of the opposite of adjacent. So what is the length of this line TM from up to down divided by the length of line MP? So that will be the as you can see in the calculation below, you can see using the tangent drawn to the curve at the point 1, 0, the gradient at the point at the point 1, 0 equals to the gradient of the tangent PT. So we are looking for the gradient of the tangent PT, and that will be equal to TM over PM, and that's what the value of TM is 2 and the value of PM is 2. That will be 1. So that means in this at the end of the day, you have your gradient of the line of the tangent. The gradient of the tangent is given as 1. So you can see that this question is a very good demonstration of how you can be asked to calculate the gradient of a line at the particular point of a curve at a particular point. Now let me talk about another part of gradient which you need to understand sufficiently. Now the next part of gradient we're talking about is limits. Now limits, when we talk about limits, a limit is basically when you say you have a limit, it's basically that is the end point, that is the maximum or the minimum value which you have to reach before you achieve a particular condition, right? That is in literal and in layman terms. But in mathematics, a limit is basically that edge of a point, that value that is just touching that point, or rather at the point, it could be at the point, or rather just touching that point, or that value that is very close to that point, or which is exactly on that point. That is the limit. So in calculus, we make use of limits because we have to talk about the points where these tangents touches the curve at, and in this point where the tangent touches the curve, we need to talk about that exact point and no other point. So that's why we make use of the limit to that point. So the limit is basically that tangent, the limit of that tangent, it will be the gradient of that tangent. That's the limit. So the limit is the tangent which is drawn through a particular point, and you can see that in this diagram that is on the screen, you can see that actually this point passes through the point P. You can see that as this series of tangents as they approach that point P. So as they approach point P, Q also approaches P. So you can see that first of all, the first line you have it as it is the one with the steepest line. The steepest line, it is the one that is furthest away from the tangent. So when you're looking for the gradient of this point, and when you make use of that tangent, you know you'll be very inaccurate because it does not pass only through point P. It passes through P and point Q. Now, but when it gets closer, when it approaches the point, when it approaches the tangent of at the point P, you have the segment PQ1, and then when it approaches again, you have segment PQ2. When it approaches again, you have segment PQ3. When it approaches again, very close, you get segment PQ4. Now this segment PQ4, it is very close. So if you calculate the gradient of that tangent which passes through segment PQ4, it will be very close to the actual value, but it is not equal. So that is what limit is about. So the reason why we make use of limit is that in mathematics, it's not possible for us to be extremely accurate. Even when making use of computational simulations, it is still not possible to be accurate and to be able to hit that point on the head. So in this case, you make use of limits because limit is basically a sufficient approximation in the real life, because even our word in our words, your measurements can never be completely accurate. You have to make use of approximations. So another reason why we make use of limits and not accurate values in calculus is that we want to talk about limits. Limits was the concept that was used in when calculus was first introduced, and calculus was introduced by Isaac Newton and some other scientists in the early centuries. Now, in this period of time when they were introduced, calculus, there was no computational simulation, there was no computers to perform calculations. So, but nowadays we have computers to make it very accurate. So most of the time when they were deriving all these formulas, they didn't have the provisions to be extremely accurate. So that is why that is another reason why I think we make use of limits today. But even though we make use of limits are extremely accurate, and even these approximations, they approach the particular values with precise nature. Now that is why when you make use of your graphical method to calculate your gradient of a line, you will get a value that is very, very close if you follow the procedures. Now in this same case, when we the actual truth is that in real life it's not very possible to be able to get the exact value of that gradient of a line at a particular point, because even when you make use of graphical method, your line will still pass through a slight point that is adjacent that that required point. So if you are looking for the gradient of a point P, you will still pass through another slight Q that is very, very close to point P, and so as such you will not be able to get the exact value. So I hope I've been able to make you understand what the word limit means. So limit doesn't mean we are wrong, but limit only means that we are making use of a very close approximation, and this approximation is the closest approximation possible in mathematics. Now, when we get to the closest limit, that is when we pass through only P. In this diagram, you can see that at the closest limit, you have your tangent as npt. So that is the one that is the that is the least steep tangent, and as such it is the one that gives us the most accurate value of the gradient of this particular curve at the point P. Now basically, I hope you've been able to understand that explanation of gradient, and let's move on to the next section. We've talked about limits, and we are going to be using that knowledge of limits to move on to another part of this episode on calculus. And in this part, we'll be talking about this is an example which says a regular polygon of n sides is inscribed in a circle. Now, what is the limit of the polygon as n tends to infinity? Now, in this particular question, we are told that the irregular polygon of n sides is inscribed in a circle. And as you can see from this diagram, as the number of sides n increases, the polygon begins to resemble what? A circle. So simply, the answer to this question is that as the number of sides approaches infinity, so that shape, that polygon approaches a circle. So that means the limit of the polygon as n tends to infinity will be equal to a circle. That's the solution of this particular question. Now this question, it demonstrates limits, and let's move on to the next part of this video. Let's talk about something a little bit higher than that. And here we're going to be talking about the gradient, how to make use of applying that limit to calculating the gradient of a curve. Now, I will give an example on the screen now. So now we have find the gradient of the curve y equals x squared at 1, 1. Now we're looking for the gradient of this curve at 1, 1, the curve on the screen now. Now in this particular curve, we are going to make use of the idea. The idea of a tangent being the limit of a chord is used to find the gradient of the curve at y equals x squared. In figure 10.5, P is the point 1, 1 on the curve, and that curve is y equals y squared, y equals x squared rather. Now we have Q is another point on the curve at 3, 9. As you can see on the curve, Q is another point that is above that point P. But now you are looking for the gradient of the point P, right? So now, as the chord PQ rotates clockwise about P, Q moves along the curve to Q1, which is the point with coordinates 2, 4, getting nearer to P. By studying the behavior of the gradient of PQ as it rotates, the gradient of the tangent as P may be deduced. Now, what we've talked about right here now, we are trying to emphasize on the fact that as you rotate the the tangent or the line which passes through the point which you are to look for the gradient, as you rotate that line, we are going to get a value that is very, very close to the gradient, and it is often equal to the gradient approximately. Now, as you can see in this particular curve, when you rotate that chord, when you rotate it chord to approach that point P, the closer it is to P, we'll be able to understand more accurately the accurate value of the gradient at P. So, and in this case, the gradient at P will be 2. So now this is just an example of how to use the knowledge of limits and the tangents at a point to calculate the gradient of the curve at that point. Now moving on, let's move on to another section of this video. This will be another example I will give, and this second example is about the tangent. So we're looking for the tangent in figure 10.5. The tangent, if the tangent in figure 10.5 is drawn at 3,9, deduce the gradient of y equals x at this point by taking the x coordinate of q as 3 plus h. Now, in this case, what we are doing here is we are going to make use of the fact that that h is a change. So that 3 was the x coordinate of the curve at 3,9. So when we add 3 plus h, that means h is assumed to be a very tiny change in the, and basically, if I have not mentioned this earlier, make sure you understand that differentiation and gradient is all about the change. I've talked about that in the beginning of this video. Now in this example, the point 3,9 replaces the point 1,1 as discussed earlier. So now we are no longer looking for the point 1,1. We are still making use of the curve y equals x squared as in the previous example. But this time we are moving our focus to a new point on that same curve. And this new point is the point with coordinates 3,9. And now we have our ON is 3 plus h and our NQ is 3 plus h squared is equal to 3 plus 6h plus h squared. That is the y coordinate, because y equals x squared. So when you square the value of x, you get the y coordinate. Now, moving on, PR is equal to ON minus 3, that's h. So that's PR is the change. PR is change in the values. Then we also have that RQ is NQ minus 9, that's 6h plus h squared. Now the gradient of PQ is the limit of at which the line segment PR approaches 0. So the reason why the line segment PR approaches 0 is that that tangent, it approaches a point. It approaches the point which is required. So that means the difference between those two lines, those 2 points on the curve, those 2 points will merge into one. So if it was touching the curve at 2 points, it will now begin to touch the curve at 1 point. So the reason is that a tangent touches a curve at only 1 point. That is why the PR approaches 0. So that PR is the distance between those 2 points. When you match 2 points, their distance approaches 0 or is equal to 0. So with this simple analogy, you should be able to understand completely that the limit of the limit, which is the gradient of that of the curve at that point, is when you divide through, you get limit as 6 plus h. So that's limit 6 plus h. And then when you say h approaches 0, so you can subsequently substitute that h equals 0, right? So if h equals 0, you have your answer as 6. That means if the limit of 6 plus h as h equals 0, so you just substitute the value of h and calculate your expression. So in this case, our value is 6, and then we'll now conclude that the gradient of the curve y equals x squared at the point 3,9 is 6. Now this is a very handy illustration of how calculus works, and I hope you understand the example. Now that is that for the gradients. And now you notice that since the beginning of this video, we've been dealing with gradients of points, but we've not dealt with gradients of a function. Now a gradient of a function, you can also express it as a gradient function. Now this gradient function, it is basically a general expression. It's not just the gradient of one point in the curve, but it's the gradient that it expresses the gradient of every point in that curve. So every gradient function is unique to a particular curve or unique to a particular equation. So every function has its own gradient curve, and there's a way you can derive those gradient curve. But now the gradient function is basically gotten when you derivate a function, or rather when you look for the derivative of a function. So the gradient curve is given by the derivative of that particular function. And for example, if you make the y the subject, if you make your subject as your y, that means that y equals So that is the function. When you derive that function with respect to x, then you get the differential coefficient of your y with respect to x. So that's what I'm trying to say. And all I'm trying to say here is that this expression, it just helps us to calculate the gradient of a particular point, or different points on the same curve. So now generally we have that the gradient function is represented as the gradient of the gradient function is the gradient equation is represented as change in y with respect to change in x. Well, then the differential coefficient is represented as dy dx. Now what I'm trying to say here is that when we talk about a line, depending on whether it's going up or going down, we can calculate the gradient. When a line in a function is going up, the gradient will be positive, but when the line is coming downward, the gradient will be negative. So that is that for the for this. Then let's take an example on that that particular aspect of gradient. So in this particular example, let's talk about the if y is equals to x squared, x cubed, find the derived function dy dx. So as you can see, this derived function is basically an expression of the differential coefficients, or the derivative of y with respect to x. Now in this case, in this example, what we'll be doing here is that we'll be saying let x increase to x plus change in x. Now this change in x is that tiny amount by which x is increased, and that change in x is basically, when you say x plus change in x, is the expression of the x coordinate of that point that is very close to your point, and that's your point is the point which you are looking for the gradient of. Now the new point is the point which is very close to it, and when you draw a tangent through those 2 points, it will be approximately equal to the gradient of the tangent through a single point. So what I'm trying to say is that that change in x will approach 0. So in the whole of in the whole creed and the whole in the whole principles of calculus, all it means and all it implies is that that change in x must approach 0. So when that change in x approaches 0, we can easily make our assumptions, our approximations, and we can still get an accurate answer. So that is what calculus is all about. I hope you understand the principle, and if you are enjoying this video, don't forget to share, to like, and to subscribe to this channel to encourage me to continue to post content like this. Thank you. So now in this question, continuing from the question, we have that where change in x and change in y are very small. So these changes are very tiny changes. And now then, if y equals to x cubed, then we can say that when you have that as a first point, then your second point, you add together your changes of your x, your respective changes in x and your respective changes in y. So that means, so when you add the respective changes, you are going to get the new coordinates. So for the next point, you have that y plus change in y, which is the y coordinates of the second point, then equals x plus change in x, which is the x coordinates of the second point. Then when you cube that, you get a new expression. So when we open that up, when we evaluate that, so that we have change in y equals x plus change in x cubed minus x cubed. So in this case, you are going to subtract you are going to look for the difference in the coordinates. So basically, you are going to say when you subtract that second equation from the first equation, so rather when you subtract the first equation from the second equation, you get this change in y equals x plus change in x cubed minus x cubed. Then when you evaluate your expression, you will have this new expression. When you divide both sides by change in x, you will have change in y over change in x equals 3x squared plus 3x times change in x plus change in x squared. Now this new expression is the kind of like the gradient of that line, and this gradient of this curve is not yet a gradient function. It is kind of like a it is like the let's call it the expression of the gradient, but we have not taken the limit. We have not assumed that change will be 0. So now the next stage we'll do is we are going to assume that let that change in the 2 points be 0 in such a way that those 2 points are assumed to match together. So if those 2 points match together, the change in their distance becomes 0. So that change in x, which is the change in their distance, when it approaches 0, anywhere in the equation that anywhere in the gradient equation that you get your change in x, you are going to substitute 0 for change in x, because this is an approximation. Now when we do that, we have the limit at which change in x approaches 0 of change in y divided by change in x equals 3x squared. Now because we have substituted for every every instance of change in x will substitute 0. Now this limit is said to be the derivative or the differential coefficient of y with respect to x. So it is just the amount by which y changes when x changes by only a very infinite amount, or rather you can say the amount by which y changes when x changes by 1. Or rather, when you say x changes by 1, that means the change is actually there's no change. So that means it is a relative or comparative change between the change in y and the change in x. It is kind of like a ratio. Now at the end of the day, our differential coefficient or our derivative of this curve is 3x squared. Now thank you for seeing me through that example, and I hope you've been able to understand that. So moving on to the next part of this video, let's talk about something else. And now we are going to emphasize on the fact that you don't actually need to go through this lengthy process of calculating the derivative of a function, because now we've actually done everything in an approximation, and then when you outline the steps of this process, we've formed it into a shortcut, and this shortcut is basically the formula for calculating the derivative of any equation. So and that formula is equals to, we'll get the formula for calculating the equation of a line. So now we have that in general, if y equals x raised power n, that means the derivative of that line is equals to n raised power x raised power n minus 1. So that shows that when we walk through everything, so let me show you how that is true, because from walking through the exercises we've seen so far, you can see that when we look for the derivative of x squared, we will get it as 2x. Derivative of x cubed is 3x squared. Derivative of x raised power 4 is 4x raised power 3, and so on and so forth. So you can see that as you can watch this trend, you can see that in general the derivative of y equals x raised power n is equal to n times x raised power n minus 1. So that is this new expression, this expression that we have here. It is used to calculate the derivative of any function at all. So now this is an example. So the derivative of x raised power 5 will be what? That will be 5x raised power 4. So this is how it is done. So and now finally we've been able to look for an expression to calculate the differential coefficient of any function that we are given. That is kind of like a very wonderful thing. Now moving on to the next part of this video, let me give an example on that aspect. Now this example, we are asked to find the differential coefficient with respect to the function. So now when we're looking for the differential coefficient of with respect to x of the function, y equals 4x cubed plus 2x squared minus 3x plus 4. Now there's a rule in differentiation that says that the derivative of a sum is equal to the sum of their derivatives. So what that means is that anytime you have a sum of numbers of sum of terms in as an equation, for example, you have the sum of 4x cubed and 2x squared and minus 3x and 4. When you sum all those expressions, you will get a new term. Now the derivative of this whole term is equal to the sum of their respective derivative. So what you do is you are going to derive the 4x cubed. Derivative of 4x cubed is equal to 4 times 3x squared, which is 12x squared. Derivative of 2x squared is equal to 2 times 2x raised by 1, which is 4x. Derivative of minus 3x is minus 3 times x raised by 0, which is minus 3. And then finally the derivative of 4 is what? Can you guess? Derivative of 4 is 0. The reason is that the derivative of a constant is 0, because as I mentioned earlier, the derivative measures the change in a value of a particular curve or a particular point. Well, in this case, when you are talking about a constant does not change in value. A constant is constant, so that means the change in that value is 0. So that means, in other words, the change, which is the derivative, is 0. That is why the derivative of 4 and indeed any constant is 0. Now in this question you have that finally your dy dx equals 12x squared minus 4x minus 3, and that is the expression for looking for the derivative of this function. Now thank you for following me through this video, and the next things we'll be doing in this video, we'll just be talking about the applications of derivation, and we're going to be talking about the summary. So now before we talk about that, let's talk about the applications of derivation of derivative. And these applications, they involve when you are looking for the when it involves the change, anything that involves change. For example, let me give an example. In physics in secondary school, you talk about the fact that the velocity is a change in this distance with respect to time, right? Now you can anything that involves change, you can always involve differentiation in it. So that means you can always apply differentiation in velocity, and even acceleration, which is the change in velocity with respect to time. You can also apply differentiation to that. There are many things, anything that involves change, even if I'm not able to mention everything in this question, you can always use it to calculate the change. So, and these changes, they are always about differentiation. So anytime you see those questions like this, doesn't matter, always know that you can always derive that function. So I will give an example. Now in this example, we are asked to find the after 2 seconds a particle has traveled a distance s meters. So this example right here is so it has traveled a distance of s meter, where s is minus 17t plus 15t square minus t cube. When is its velocity 0? When it is its acceleration 0, find the velocity and acceleration after 2 seconds, 6 seconds, 10 seconds. Now in this question, it's not very difficult. All you need to do is you are going to express the function, and then you are going to derive that function. So if s, which is the distance, equals minus 27t plus 15t squared minus t cube. So when you derive that, you have your derivative of your distance is equals to minus 27 plus 30t minus 3t squared. And then we are asked to look for the now this velocity is equal to the change in distance with respect to time. That means the derivative of your distance is equal to your velocity, and the derivative with respect to time. So that derivative is the derivative with respect to time of your distance is equal to your velocity, and in turn your derivative of your velocity with respect to time is equal to your acceleration. Now in this question, all you need to do is, when you're asked to what is the when is its velocity 0, all you need to do is you equate that equation to 0. So as you can see here, so we equated that to 0. So the vdt is equal to 0. So when we equate that to 0, so okay, rather the vdt is the expression for acceleration, because acceleration is the derivative of velocity with respect to time, right? That means acceleration expression is 30 minus 60. So all you need to do is you equate the velocity graph to 0, then you solve for your time by making use of your quadratic methods of solving equations, and then that is how it is done. Yeah, it is 0. The velocity is 0 after 1 second and after 9 seconds. So you have t is equal to 1 and t is equal to 9. Now I won't solve the entire question because of time in this video. So this video is getting extremely long. So let's move on to the next part of this video, which we're talking about the summary of all the concepts we've introduced so far. Now so far we've talked about the fact that a function of x tends towards a limit k if function of x minus k approaches 0 as x approaches some value which is a. So that is number 1. Then number 2, what we've talked about the fact that the gradient function of a curve is used to find the gradient of a given curve at a given point. Now that's the second thing we've talked about. Then next we'll talk about the fact that the dy dx is a differential coefficient for the right function or the derivative of y with respect to x. So it measures the rate of change of y compared to x. So as you can see, it's a comparative value. It's like a ratio, like a fraction that compares the change with the y and the x values. Now next, let's talk about the short formulas. So if y equals a x raised power n, then dy dx equals a n x raised power n minus 1. That is the formula for calculating gradients. So of any expression. Then we have, if y equals x raised power minus n, then dy dx equals minus n times x raised power minus n minus 1. So all you need to do is, when you are looking for derivative, all you need to do is, of a function, all you need to do is you multiply by the power of your x or your or the variable with respect to which you are making your derivation. So in this case, the reason why we are multiplying by the power of x is because we are derivating with respect to x. So if we're derivating with respect to t, we'll multiply by the power of t. So you can see we are multiplying the power of x, and in the first time our power of x is n, in the second our power of x is minus n. So multiply by minus n, and then at the end of the day, after that, what you do is you now decrease the value of that power by 1. So basically that is why the gradient of y equals x raised power minus n is equals to minus n times x raised power minus n minus 1. So decrease by 1. That is why it's minus x minus n minus 1. So this is just it. Then if y equals k, where k is a constant, that means the derivative is 0. as you can see. Then number 5, if y is a function of t and t is a function of x, that means dy dx equals dy dt times dt dx. So this is called the chain rule. So all you need to do is, if y is a function of a function, so if y is a function of a function, so all you need to do is you need to look for the derivative of y with respect to the first function, and then look for the derivative of the first function with respect to the second function. So when you multiply those together, you get the derivative of the entire function with respect to the first function. So with respect to the second function. So that will be dy dx equals dy dt, which is the first variable, times the dt dx. So now we have number 6, given u and v as function of x. So if y is uv, then dy dx equals v du dx plus u dv dx. So this is called product. Sorry, it's called it's called product rule. Then if y equals u divided by v, then dy dx equals v du dx minus u dv dx over v squared. So this is called the quotient rule. And finally, we'll talk about the fact that differential calculus can be applied to solve problems involving gradients, velocity and acceleration, turning points, curve sketching, and may be applied to real life problems. So as I showed in the example I gave. So that is the end of our video, and for those of you who are hungry for more knowledge on calculus, I promise that in a subsequent video in this channel I will talk about it in more advanced detail, where we're talking about curve sketching and all these other advanced parts we'll talk about. So but today this is as far as we can go. Thank you for watching, and see you next episode.